Today I will be teaching you how to perform basic stoichiometry. Example 1. Ethylene, C2H4, can be burned in the presence of oxygen gas in a typical hydrocarbon combustion reaction. If you start with 45 grams of ethylene, C2H4, how many liters of carbon dioxide gas will be produced at STP? The first thing you want to do when solving a stoichiometry problem is write the chemical equation. Your biggest clue to writing the chemical equation is hydrocarbon combustion. In hydrocarbon combustion reactions, you know that there will be a CH and O on both sides of the chemical equation, both reactants and products. You also know that the products will be CO2 and H2O, otherwise known as carbon dioxide gas and water. When writing the chemical reaction, you can go ahead and write the products until you figure out the reactants. So you can go ahead and write CO2 and H2O as products. In all combustion reactions, you add O2 to whatever you are burning. In this case, you are burning ethylene, C2H4. So you now know that your reactants are C2H4 and O2, which is also fire. Now that you have written your chemical equation, you must balance it. You want to balance chemical equations using the acronym MENO. MENO stands for metal, polyatomic ions, nonmetal, oxygen, and hydrogen. The first thing you want to look for is nonmetals in this equation, which is carbon. You must have the same amount of carbons on both sides of the chemical reaction. Because you have 2 carbons on your reactant side and only 1 carbon on your product side, you must add a 2 coefficient to the CO2 to make your carbons balanced. Next, you would want to skip oxygen since it is in 2 places on the product side, which would make it harder to balance, and go straight to hydrogen. You have 4 hydrogens on your reactant side and only 2 hydrogens on your product side, meaning you would want to add a 2 coefficient as well to H2O or water. Now, last but not least, you want to balance your oxygens. You only have 2 oxygens on your reactant side, but you have 6 oxygens on your product side because you have O2 times 2, which is 4, and 1 times 2, which is 2, so 4 plus 2 is 6. You can divide 6 by 2 and get 3, adding that coefficient, and you can add a 1 to C2H4, making your reaction completely balanced, as 1 C2H4 plus 3 O2 yields 2 CO2 plus 2 H2O. Now you are ready to begin setting up your dimensional analysis part of the stoichiometry. Here is the chart you will need to reference regarding the things you are looking for and things you have in the reaction. This chart, however, is much bigger, but is reduced for the purposes of this video. The first thing you want to start with when setting up your stoichiometry dimensional analysis is the amount it gives you in the problem. It gives you 45 grams of ethylene C2H4, but you want to get liters of carbon dioxide. So you have to first start with your mass of A, which is 45 grams of ethylene, go to moles of A using molar mass, go to moles of B using the molar ratio, and then finally go to volume of gas B, or carbon dioxide, using 22.4 liters per mole. So when first setting it up, you want to use 45 grams C2H4 and that is over 1. When doing dimensional analysis, in order to cancel things out, you must put them on both the top and bottom. So grams of carbon dioxide, grams of ethylene will now go on the bottom of your chemical reaction. And since you need to get to moles, 1 mole of C2H4 will go on top. So in order to get from grams to moles, you want to use the molar mass. Molar mass is used with the mass on the periodic table. If you look here, carbon has a mass of 12.01 and hydrogen has a mass of 1.01. You want to then find the molar mass of ethylene using 12.01 and 1.01. However, you don't have only 1 carbon or only 1 hydrogen, so you have to multiply the mass by however many you have using the subscripts. You have 2 carbons, so you want to multiply 12.01 by 2, which equals 24.02. The next element in ethylene is hydrogen. The mass of hydrogen is 1.01. Your subscript on hydrogen is also 4, so you have to multiply 1.01 by 4 to find the total mass of hydrogen. This equals 4.04. Finally, to find the total molar mass of ethylene, or C2H4, you must add the individual masses of carbon and hydrogen, or 24.02 and 4.04. This then equals 28.06 grams, or your molar mass of C2O4, or H4. Now that you have 1 mole of C2H4, you can now get 1 mole, or moles, of carbon dioxide using your chemical equation. You use this using the molar ratio. As said before, what you have on the top, you must have on the bottom to cancel out. So you have to have moles of C2H4 now on the bottom. And since you want moles of CO2, you would then put that on top. You find the molar ratio using your chemical equation, using the coefficients. There is a 1 coefficient before a C2H4, so you only have 1 mole C2H4 in your dimensional analysis. However, you have a 2 coefficient in front of CO2, meaning you have 2 moles of CO2. Finally, you look back up at the problem and realize that you need liters of carbon dioxide gas instead of moles. So you now have to convert 2 moles of CO2 into liters. You do this by using this expanded mole chart and know that 22.4 liters equals 1 mole. So that is the next thing you do in your dimensional analysis. 22.4 liters of CO2 over 1 mole of CO2. You then check your dimensional analysis problem to make sure you ended up with what you needed. You have grams of C2H4 on the top and also grams of C2H4 on the bottom, meaning they cancel. You have moles of C2H4 on the top and also moles of C2H4 on the bottom, which means they also cancel. Finally, you also have moles of C2H4 on the, or CO2 on the top and moles of CO2 on the bottom, meaning they cancel, and finally you're left with liters of CO2, which is what it asked for in the problem, liters of carbon dioxide gas. You now solve the dimensional analysis problem by typing it into your calculator. There are two ways to input this dimensional analysis problem into your calculator. The first way, if you have a TI 83 or 84, is the fastest, but also more complicated, in my opinion. What you want to do is set up a fraction. You do this by pressing the alpha or alphabet button in y equals. This then gives you a list of options. You want to choose numerator over denominator, or n over d, using enter. You now have a fraction set up. You then want to use parentheses both on the top and bottom when multiplying across, so that the calculator knows to multiply across on the top and bottom before dividing. You then input your numbers, 45 times 1 times 2 times 22.4, close parentheses, and you do the same on the bottom with the bottom numbers. 1 times 28.06 times 1 times 1, close parentheses. Enter. You then have your answer. However, if you do not have an as advanced calculator, you can do this in a series of steps. First, you would want to multiply the top numbers. 45 times 1 times 2 times 22.4. This gives you 2016. You would then want to multiply the bottom numbers, 1 times 28.06 times 1 times 1, which gives you 28.06. You would then want to divide 2016 by 28.06, which also gives your answer of 71.846,04419. And that is how to input this dimensional analysis problem into your calculator with both advanced and unadvanced calculators. The answer it gives you is 71.846,04419. However, this is not your answer because you must round to the appropriate number of significant figures. When calculating your significant figures, you always want to round to the least number that occurs in your problem. However, you do not count this one or any of the moles in significant figures. 22.4 has 3 significant figures. 28.06, however, has 4 significant figures. And 45 only has 2. This makes 2 your least amount of significant figures, meaning you must round to 2 significant figures. 71.8 would round to 72 because 0.8 is greater than 5, making it more accurate to round to 72 than 71. You must then put your unit on 72 as to not leave it blank. Since you were asked for liters of carbon dioxide gas in the problem, that is what you're ending with, 72 liters CO2. Making your answer 72 liters CO2 at STP. At STP is not typically important, but is often seen and nice to know. You have now finished your first stoichiometry problem and are ready to start more. Good luck.